Welcome to today's ACM talk. This webcast is part of ACM's commitment to lifelong learning and professional development. It serves a global membership of computing professionals and students. My name is Gideon Uchehara. I am a PhD graduate at the Department of Electrical and Computer Engineering at the University of British Columbia, and also a quantum intern at PsiQuantum. I work on quantum algorithms, compilation, and architecture-aware optimization. My research interest is in circuit cutting, qubit reuse, and high-fidelity generalized measurement. You can find more of my background in the resource section of the console. For those of you who may not be familiar with ACM or what it has to offer, here is more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. You can see more of the highlights on your screen. ACM provides access to ACM Digital Library, the world's most comprehensive database of computing literature, leading publications, and global conferences that draw top experts on a broad spectrum of computing topics. It also provides support for education and research, including curriculum development, teacher training, the ACM Turing, and ACM Prize in Computing Awards. Also, it provides the ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in professional practice. Before we get started, let's quickly do some housekeeping. First, if you have questions at any time, please type them in the Zoom section. There's a Q&A button. Using the Q&A button, and also we'll organize the questions as Mariia speaks and try to get as many questions as possible. This session is recorded and will be archived. So you will receive an email notification when it becomes available. And you can also check learning.acm.org for updates on these and other upcoming webcasts. At the end of the presentation, you will see a survey open on your screen. Please take a minute to fill it out to help us improve our talks. Today's presentation is Quantum Programming in Depth, bringing software engineering practices to QC by Mariia Mykhailova. Mariia Mykhailova is a principal quantum software developer at PsiQuantum, working on software for fault-tolerant quantum computation. Prior to that, she was a quantum software engineer at Microsoft Quantum, joining the team in early 2017, just in time to participate in development of the first version of the quantum programming language that became Q#. Mariia created the Quantum Canvas project, an open source collection of hands-on tutorials and programming problems for learning quantum computing. She's also a part-time lecturer at Northeastern University. She teaches Introduction to Quantum Computing since 2020, and also the author of the O'Reilly book, Q# Pocket Guide, and the Manning book, Quantum Programming in Depth. Mariia, without further ado, take it away.
Thank you for the introduction, Gideon. Hello, everybody. As you just heard, my name is Mariia, and I will talk to you about quantum programming and how it can support our work on more broad quantum computing, and how we can bring the best software engineering practice to our quantum programming work. A quick outline of what I'm going to talk about today. First, a little bit about myself. So basically duplicate the bio that Gideon just shared, but with pictures. Then I'll start with the topic that is probably the most interesting. What kinds of problems can quantum computing solve? What kinds of things we look for when we talk about quantum computing solving problems? Then I'll go a little bit deeper into how we compare performance of quantum and classical programs, because this is key to figuring out whether a problem is going to be good to solve using quantum computing. Then I will finally get to quantum software development workflow and talk a bit about how we test and debug quantum programs. After that, I'll show you an example of snapshots of how a quantum software development workflow looks like using PsiQuantum software tools that I'm working on. And finally, I'll wrap by sharing some really good quantum programming and quantum computing learning resources that I developed myself. So with that, let's go. So a bit of introduction to my quantum computing career. So by training, I am not a physicist. I am a classically trained software engineer. Doesn't mean Latin and violin, means a master's degree in applied math from Ukrainian university. So a lot of math, a surprising amount of physics, but very little of it quantum, and a little bit of software engineering. I spent some years working on classical software, but my quantum software engineering journey started in 2017 when I joined Microsoft Quantum. And basically everything I learned about quantum computing, I learned since then. So I worked a little bit on C# programming language. And then after it got released, I veered into education and outreach. My first project there was called Quantum Katas. So you can see a screenshot of one exercise from them right here. So the idea is you have a well-defined problem in quantum computing. It can be very simple, can be slightly more complicated. And you have the code that you need to fill with what you believe is your solution to the problem. And best of all, they come with tests. So when you have a solution, you can run the test to figure out whether it is actually correct. You get immediate feedback, which is extremely valuable if you are learning on your own and not in a classroom setting. So that rather started my education career. So I spent a couple years developing that project, doing all kinds of hackathons, workshops on quantum computing. In 2020, I started teaching quantum computing at Northeastern University. Still do that 5 years later. And then I finally got the opportunity to write a book, which is something I wanted to do since I was a kid, but I never knew what this book would be about. So it turned out it would be about quantum computing. So C# Pocket Guide in 2022. And after that, I veered slightly into algorithm implementation and resource estimation. We will talk more about this in a couple of minutes. And then in 2025, this was a big year for me, and it's not even over yet. I moved from Microsoft Quantum to PsiQuantum, a startup that works on full stack quantum computing, and published my second book that I will also talk about a little later. Now, this background makes me very attuned to the quantum software area. So this is where I work, and this is what I'm most interested in. So what is the role of quantum software in the whole stack of building a quantum computer and running a quantum algorithm on it to solve some problems? Now, of course, one part of the answer is just enabling this, just being able to implement the quantum algorithm and translate it into commands that the quantum computer will be able to understand and apply, and then get back the results. But there is another part of the answer, which is something that you can do even before you have a quantum computer to run your algorithm on. But to dig deeper into this part of the answer, we first need to talk about what kind of problems we are looking at for quantum computers to solve. Now, if you are here, if you are curious about quantum computing in general, you probably heard things about what kinds of problems quantum computing is going to solve. One of the very good examples, very good educational examples, I should say, is Grover's search algorithm. It is an algorithm that solves the search problem. Basically, you have a function that can take value 0 or 1. In other words, you can ask a question about some input, and you will know whether the answer to this question is yes or no. But this is the only way you can get information about your question. You don't know how this function works inside. And the goal is to find an input for which the answer will be yes. Of course, we want to do it as fast as possible. Now, in a classical setting, the only solution is basically brute force. You know nothing about the internal structure of this problem. So the only way you can solve it is just keep asking questions about different inputs until you get a yes. Brute force solution, very inefficient. In quantum computing, you can do this faster. Roughly speaking, instead of going through all elements and making as many queries as there are possible inputs, you can do this in square root of the number of inputs queries. Not going to go into more details here. This is not why we're here. But we have this theoretical advantage of a quantum solution over classical one, described in terms of the number of queries to our function. This is what we call comparison of asymptotic behaviors. We separate one aspect of our solution, one way to quantify how much of a certain resource it consumes. And then we compare a classical solution with a quantum one in terms of this resource. In this case, the number of queries to our function. What we get in a result is a comparison of asymptotic behaviors that is going to look something like this picture. So we have a classical solution, which takes a certain amount of resources that grows somehow as the problem size grows. And we have a quantum solution that also has some pattern of consuming more resources as the problem size grows. The trick is, what kind of resources should we be thinking about? Turns out we shouldn't be thinking in terms of very abstract resources, such as the number of queries to our function, the way search problem does. Instead, we should take our analysis further. We should consider more practical aspects of resources. A very, very good example is just the raw time it would take to solve the problem. From the beginning of when you ask your computer to solve this problem, when is it going to return to you the solution, the answer? And when we think in these terms, it becomes more clear which problems are good for quantum computing and which ones are not so good. Because when we have a picture like this, we are going to have a crossover point, most likely. At some point, we are hoping that quantum solution is going to become better than classical solution. For very, very small problem instances, it never happens that quantum solution is better than classical, just because quantum computers on their own are slow. So we're always going to start like this. Small problem sizes, quantum solution is slower than the classical one. But we are looking for cases in which eventually a quantum solution outperforms the classical one, becomes faster. And we are also looking for problems in which our problem instances are in this area, in the area in which quantum solution is actually faster. If quantum solution is only asymptotically faster, but to actually get to this crossover point and beyond it, it takes insanely huge problems that we don't have, or that are fundamentally impossible to run even on a quantum computer. Then this solution is not going to give us practical advantage. We get practical advantage from quantum solutions only if this area where quantum solution is a lot better than the classical one is in the area of problem instances that we actually care about. And it turns out that the search problem, for example, is not actually a good candidate for quantum computing because its speed up is not sufficient. Why does this happen? Right, I will talk about why in the next slide. So when we compare performance of quantum and classical programs, we should not compare their asymptotic behaviors. I mean, we absolutely should do this as the very first step. If the theoretical quantum solution is worse than the theoretical classical solution, we don't even need to go there. It's not going to get better. But if we got a theoretical quantum solution that has better asymptotic complexity, like Grover search, we don't stop analysis at that. Instead, we implement the quantum program and we evaluate what its performance is going to look like when it runs on a fault-tolerant quantum computer. And then we take that evaluation of how long it will take to run this problem, and we compare that with our baseline, the best classical solution for this problem. Now, if this comparison is in favor of the quantum program, if even with how slowed down it is, it still beats the best classical solution we can think of it. Well, this is a sign that we got our quantum advantage, or that we will get it once we actually can run this program on a quantum computer. Now, why quantum programs are slow. There are several reasons for this. But ultimately, when you are thinking about something like querying a function on a computer, one single query to a quantum computer is going to be much, much slower than a single query on a classical computer. There are several reasons for this. First, you probably heard that quantum computers are noisy, which means that we need to run error correction on them. So every single logical gate or measurement, which are the primitive operations you can do on the qubits, is in fact implemented as a whole series of gates and measurements, just to be able to get rid of the effects of the noise on our computation. So this is a massive source of slowdown. Second, the physical quantum gates, the ones that your quantum computer actually executes, are slower than the primitive gates in classical computing, just because they're different processes. And third, there is a limited set of gates that a quantum computer is going to be able to do. So instead of just applying whatever gate you need, you have to decompose most of them into sequences of gates that your quantum computer can actually do. And sometimes it's going to be an approximate representation, which is going to involve a really long sequence of gates, some of them obtained in a special manner that is going to slow down execution even further. And those factors both slow down program execution and increase the size of the physical quantum computer you need to be able to execute it. So this is the lesson I want you to take out of this. Quantum programs are slower than classical ones. So we have so to get our quantum advantage, we need quantum algorithms that are much, much, much faster than best classical solutions for the same problem. And we need to actually do this analysis in terms of how fast the program will complete on a fault-tolerant quantum computer, rather than just think about it in theoretical terms. And this is where the second part of the answer comes in. It turns out that we can write software and evaluate its performance on a fault-tolerant quantum computer even before we have that fault-tolerant quantum computer. So what does quantum software development workflow look like from the user's point of view? This is the area of quantum software I'm working on, creating tools that help users develop and test their quantum code. So the first step, once you figure out an algorithm for the problem, you want to develop it. You want to sit down and implement the quantum code involved in it and the classical code involved in it. Most likely there are going to be both. The second step is actually exactly the same as in classical software. You need to validate your code. You need to check that it is correct. Running on hardware, on quantum hardware, is very expensive. So you don't want to figure out that your code has a bug once you get there. So you want to do as much of your testing and debugging as you can before you hit quantum hardware. And there are special tools for this that I'll talk about in the next slide. And then, of course, if you find any bugs, you go back to step one and fix them or change your approach. Now, once you have established that your code is correct, the next step is this bit that I just talked about for 15 minutes. You need to figure out whether this solution is going to be good enough. You need to estimate its performance. You need to basically figure out how many resources it's going to need, both in terms of how many qubits, so how big a quantum computer you need to run it, and in terms of how long it's going to take. Because you know how it is. If you go to meetings with your boss for a year and you keep telling them, well, my solution still works, it's not going to go very well. You want to get your answer in a reasonable time frame, so hours, days, weeks at most. And there are special tools that help you get those estimates automatically, just based on your program. And then if you figure out that, okay, this is kind of promising, but still too slow, you get those performance evaluation results and you go back to the whiteboard and you optimize your algorithm. And then again, you can implement the optimized version of the code and you can compare its performance with the performance of the original one using the exact same tools. So you can go through this loop of developing the algorithm, validating it, and evaluating its performance as many times as you need, using just the software tools, not touching hardware. Because doing software estimates is much easier, much faster, much cheaper than actually running your code on hardware. But then once you are done with this loop and you are happy that your solution is correct and that it is going to take a reasonable time to complete, then you just take your fault-tolerant quantum computer, run your program, and get your results, which you then convert into the solution to your problem. So this complete workflow is what the companies in quantum computing work on right now. But of course, different people work on different steps of this stack. Now, this is the quantum software development workflow. And one thing I want to talk a bit more about before we get to the example is how do we test quantum programs? The straightforward thing to attempt is to test your programs on real quantum devices, because that's kind of what we do with classical software. We write a program and we run it where it will run right away, most of the times. But there is a number of problems with this approach. First, real quantum devices are noisy. So if you run your program on them and you get incorrect result, you don't know whether it is the problem with your program or whether it's just side effects of noise. And even very small programs, if executed without error correction, are going to give you incorrect results much, much more frequently than the correct ones. And the second problem is that it is very hard to debug your quantum programs on a real device. Because how do you debug your program? You either insert some print statements, or you turn on your debugger and go step by step, watching how your variables change with each operation. You cannot do either of these things on a quantum device, because quantum physics actually prohibits you from doing this. You cannot take a look at the state of your quantum program the way you would do in a debugger or in a print statement. because doing this would ruin your state, collapse it, and also wouldn't give you complete information about it. And the last thing is testing on real quantum devices is expensive. More expensive than just running on real devices, because you're going to need multiple runs, very multiple runs. What we do instead? Instead, we develop specialized software tools called quantum simulators that can run your program by pretending that they are quantum computers. But in fact, they are classical programs. They only do the linear algebra and probability theory necessary to imitate what a real quantum device would do physically. And since they are classical programs, you can access their internal state just the way you do with your normal classical programs, which allows you to do things you would not be able to do on real devices, but also allows you to have your print statements and your debugging as you work on your program. Now, there are limitations to them, of course. Quantum simulators can handle either small programs, less than 30, 35 qubits, or very specialized programs. For example, programs that implement classical computations on superposition states on a quantum computer, which are actually very useful. And it is very useful to be able to test them thoroughly. But this is what we have right now for testing our quantum programs. And this is still an open question, how we are going to test our programs that are too big to fit into a simulator. A lot of very clever people look into this as one of the areas of research in quantum computing. And I hope that 5 years from now, we would have more bullet points on this slide with other more specialized and more powerful approaches to testing quantum programs. And now we have just enough time to take a look at an example. So for an example, I'm going to walk you through what things look like if I want to take a quantum state preparation algorithm and implement it and evaluate it. Now, the state preparation problem is something fairly unique to quantum computing. You are given a set of qubits and the array of amplitudes that describe a quantum state. And your goal is to prepare those qubits in this state. That's it. And the demo I'm going to show you, it's not a live demo, it's a number of screenshots. This is done using the quantum software stack we are developing at PsiQuantum. And you can see another more, probably more sophisticated demo at this link, psiquantum.com/software. So the first step is to design the algorithm, to figure out what you want to do before you implement it, of course. One of the very popular ways to do it is by developing a circuit diagram for it. And the circuit diagram is actually recursive. You apply one gate, and then you apply control versions, basically conditioned versions of state preparation on the rest of the qubits, with the first qubit as the condition. And you repeat this on the next level deeper, and so on. Once you are satisfied with your algorithm, you go ahead and implement it. When you write the code, you you write something like this. It's going to be a Python library. Workbench is a Python library that is going to provide you several specialized data types that you use to express qubits and quantum routines, qubreaks in your code. And then it is just Python code with specific methods of those types to express gates. But the neat thing is you can combine classical computation with quantum ones all in the same program. The next step, once you have written the code, you test it. And you are going to notice some familiar constructs here if you are using Python and if you are using PyTest, because your tests are going to be Python code as well, with some extra steps in them. Here, what I'm doing, for example, is I instantiate a QPU, quantum processing unit, its representation in the program. And then I allocate qubits on it. And after that, I call my state preparation routine on those qubits for a certain list of amplitudes. And now the question is how I test my program. Well, I'm going to run this program on a simulator. So I'm going to use a library call that gets the quantum state of this quantum device. This line is not going to work on a hardware device. But when I'm running on a quantum simulator, it is going to work. It is going to return to me an array of amplitudes. And then I just compare that array of amplitudes with the ones that I actually set out to prepare, again, using PyTest routines. This is it. There is no hardware involved. There is no physics involved. Just Python and some special classes to represent our quantum data types. And once I have the code that is correct, now, of course, there are going to be more types here. If one of the questions that just popped up is why are you testing on very small inputs only, that's what fit on the slide. I have more tests in it in the real repo. And the last step, once I have established that this code is correct, I'm going to consider optimizing it. And to do this, I'm going to use tools that allow us to analyze how much resources it would take to run this algorithm on a state with a certain number of qubits. And here, what I'm doing, I'm counting Toffoli gates. This is a special kind of gate that are one of the measures of the resources taken by the algorithm execution. And I am comparing two algorithms. One is the recursive state preparation that I just showed to you. And the other one is a workbench library algorithm called alias sampling. It's more complicated. It involves some classical preprocessing. The code for it is longer, but it is more performant. And this is exactly what we see here on this plot. Once we count the resources necessary to execute the algorithm, we see that the orange line, alias sampling, requires much, much less resources than the blue line, recursive algorithm. Now here we stop at 10 qubits. So technically we could simulate the programs at this point, but we don't need to take this comparison further. We could. Our resource estimation tools could give you the numbers it takes to prepare 1,000 qubit state. But we don't need to, because we see that the behavior of our algorithm is a lot worse than that of the library algorithm, even on those small inputs. So here we say, okay, this is a lovely educational algorithm, not going to use it in practice. If it was something we had ideas for optimizing, we could go back and change our previous steps and optimize our algorithm further. Now, this is more or less what I wanted to tell you about quantum software development and its role in building algorithms for quantum computers. Now, the last bit I promised to you are the two resources for learning quantum computing. Now, I'm a software engineer by training and by trade. So I really believe in learning by doing, in particular by writing programs. So here are the two resources I developed over the years. One is a very good quantum computing 101 resource, the quantum katas, the ones I mentioned in the beginning that are collection of tutorials and programming exercises with immediate feedback. This resource is free, so you can go and use them anytime. And the second one is the book I have written in the past 2 years. And yes, it did actually take 2 years, which I think of as Quantum Computing 201. Once you have learned the basic concepts, how do you make the next step? How do you think about quantum computing algorithms as whole projects with tests, with performance evaluation, with comparisons of different algorithms, both quantum and classical. So this book offers you a collection of quantum programming projects, one project per chapter, that are broken down into small steps. So each section in a chapter builds up upon the previous one and does something small that ultimately, by the end of the chapter, allows you to build the whole project, complete with tests and performance. It uses two programming languages, Q# and Qiskit. So hopefully everyone will find one of the parts to their liking. And there are plenty of project ideas that you can explore on your own that are similar to the ones covered in the book, but are slightly different. And there is a discount for it. If you go to the Manning website, the code Quantum45 is going to give you a very nice discount for the book. This is it for today. Thank you so much for attending and listening, and we are ready for questions.
Thank you very much, Mariia. Let's now move on to the question and answer session. These questions will be answered by the most upvoted question. And so the first one is, can you give examples of problems where quantum computing does better than classical computers, regardless of problem size?
I'm not actually sure there are examples in which quantum computing does better regardless of problem size. Because if we look at some of the very common example problems that are well suited for quantum computing, such as finding the energy of the ground state of the molecule. If we look at the tiniest little molecules like water or hydrogen, we can simulate them classically, no problem at all. We don't need a quantum computer for that. The challenges that classical computing faces is when those molecules become bigger, when they have more electrons, when they have metals in them, when they have dozens of atoms. So I don't have an example for you here, just because if you have a tiny little instance of a problem, classical computers are going to be better.
Thank you, Mariia. The next question is, as a beginner to quantum computing, what kind of problems can I choose to have hands-on for quantum software development? Please give me some example problems.
The ones in the quantum katas are extremely lovely for just getting started and learning the basics at the same time. The ones in the book are also lovely. The examples of problems we have there is, for example, preparing very small states. If a state has a specific shape, you don't need the general algorithm for it. You can figure out a solution specific to that state. Another example is state discrimination. If you are given a quantum state and you know that it's either this state or that one, how do you set up an experiment to figure out which of those states it is? Another example is Grover search. Now, this algorithm is not going to be practical. It's not going to allow you to search through databases faster. Please never repeat that. But it will allow you to get some practice in developing something that is an end-to-end solution using quantum computer. It's not going to be practical, but it is going to be incredibly educational.
Awesome. Thank you, Mariia, for the answer. Although this question might be linked to the answer you've given, but just so the person who asked it can get your perspective, what kind of programs are suitable for quantum, text editing, analyzing images, web search?
Neither of those. Now, the thing about quantum computing is that some operations that you consider as just given in classical computing are very expensive in quantum computing. One example of this is data loading. You probably don't pause to think about something like reading a file or loading a dictionary into your classical program. I'm pretty sure you do this kind of automatically. But in quantum computing, loading input data in some sort of quantum states that can later be used is already an expensive operation. So if you have a huge data set that you want to do something with, like machine learning or, well, any sort of data analysis, you are going to have problems just because it's going to be very expensive in terms of performance and resources used to load this data set into your quantum computer. Usually when we look at quantum computing problems that are a good fit, that are going to do better than classical, they are small input, big compute, small output problems. So basically your input has to be very small. Your computation that you do with this input data has to be very big and very hard for classical computers to do. And then your output has to also be small, because another problem that is expensive is getting the results of your computation. The example with getting ground state energy is so ubiquitous because the description of the problem is kind of small. It describes the structure of the molecule, and it's not overwhelmingly huge input, not like, the whole internet. But then the computation you need to do to get this energy of the ground state is really big and complicated for classical computers to do. And then the output is a single number, the actual energy. So this is a good fit. Anything that has huge data inputs most likely not a good fit.
Thank you, Mariia. Let's move on to the next question. Can most quantum algorithms be reduced to a Grover search algorithm? And if yes, with what complexity?
No, that's an easy one. Grover search is an excellent educational algorithm because it is relatively easy to explain, but it gives us a very little speed up. The speed up it gives us is quadratic. So if the brute force search takes n queries, Grover search takes square root of n queries. And once we translate this into something that is going to run on a quantum computer with error correction and with all the other overheads, it's going to be too slow. Any sort of algorithms that give us quadratic speed up, like Grover search, are not going to be good fits for giving us practical advantage. We need much better improvements, ideally exponential. So there is a limited number of structures of types of algorithms that give us speed up, which I'll admit I'm not prepared to discuss on the spot, but Grover search is definitely not one of them. You're looking for better speed ups than what Grover search does.
Awesome. Now, the next question is, what are the major applications of QML?
QML can have multiple meanings, actually. It can mean any combination of classical problems and quantum computing. In a sense of using quantum computing to solve classical machine learning problems with classical data, it falls into the same hole as image analysis. The inputs are huge, which means it's going to be very expensive to run any quantum algorithm on them. So right now, there is some research in QML, but I don't think I have seen an example in which we would like firmly say, yes, we get a speed up from using a quantum computer to solve a classical machine learning problem with classical data. An interesting area of research is solving machine learning tasks on quantum data using quantum computers, because if you have data that is already quantum, then you sidestep the whole problem with loading classical data onto a quantum computer. But this is about the extent of my familiarity with QML applications.
Thanks, Mariia. Next question is, are most quantum computing algorithms based on optimized classical algorithms?
I don't think so. So the quantum algorithms, they are just different. So there are parts of quantum algorithms that are based on classical. For example, it is often necessary to do arithmetic on numbers that are encoded as quantum states in superposition. So those routines are coming from their classical equivalents. But in general, you need to have a block inside a quantum algorithm that is uniquely quantum, that doesn't come from a classical algorithm.
Okay, great, thanks. Next question is, what is the current state of quantum software? How developed is it? Or has it barely started? What programming languages are being used? And what is the attitude of big tech companies towards quantum software and quantum computing in general?
Oh, this is a big one. This one I can talk about until we run out of time. Okay, so quantum software has been developing for quite some time. PsiQuantum's software stack, I think, is about a decade old, give or take. Some of the other languages in use are probably about the same. Qiskit was released for public use in 2017, and so was Q#. And I can say that Q# has been developed since 2017, Qiskit probably a little bit earlier. So some of the software stacks are about a decade old. Some are more recent. And different companies use different software stacks, of course, because ultimately each company that works on quantum computing wants to have flexibility. If they want to add some particular feature for their language, some research capabilities, some result estimation capabilities, they want to be able to just go in and do it. What do big companies think about it? There are some big companies that develop their own languages. So Qiskit is developed by IBM and Q# is developed by Microsoft, and Google Quantum has its own quantum language, and NVIDIA too. Also, we have startups that develop their own software stacks, like PsiQuantum. And as for how developed it is, they have gone quite a long way since their inception. I followed closely the development of Q#, and it changed quite a bit since the very first version. But there is, of course, still a way to go. I would say that we will be entirely happy with our quantum software stacks. Probably never. The way we are never happy with our classical programming languages.
Thank you very much, Mariia. We have a minute or two left to answer one or two questions. So the next question is, to do quantum programming, how much of quantum physics do you need to know like how much physics does he need to know, as he or she has university. The person has been in university for 20 years and nearly forgot physics learned in university. However, all these years I'm working on embedded software engineering with skills in C++ and Python.
The good news is you do not, in fact, need physics to work on quantum software. Look at me, I'm a role model. I did learn a little bit of quantum physics back in university, which was longer ago than I care to admit. But I don't use it in my job. Under the hood, quantum computing is linear algebra and probability theory. You need to know physics specifically if you work on the lowest levels of the stack, the levels that basically do control of the actual physical objects and processes that implement your quantum computer. Like, I don't know, photons or trapped ions or whatever happens in your quantum computer. If you work somewhere higher up, like if you work on the compilation stack, on user-facing software like I do, you don't need to know physics. That bit is abstracted away several layers under you. So in my work, I basically assume that qubits are mathematical constructs that allow us to do certain operations on them natively. And then once we have compiled the high-level code to those operations, we hand them off to another team. And then another team thinks what to do with that.
All right, thank you, Maria. I'm afraid we have run out of time today, and I would like to thank Maria again for her informative presentation and insightful answers to the many questions. A special thanks to each of you for taking the time to attend and participate today. This talk was recorded and will be available online shortly at learning.acm.org. You can find announcements on upcoming talks and other ACM activities at learning.acm.org and acm.org. Also, please fill out our quick survey where you can suggest future topics or speakers, which you should see on your screen in a moment. And on behalf of ACM, Maria, and myself, Gideon, thanks again for joining us, and I hope you will join us again in the future. This concludes the talk. Thank you all.
Have a lovely day.